Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 83, Figure A, shows the cross-section of a column that uses a structural shape known as W8 by 67. Which is a wide flange beam nominally 8 inches deep, weighing 67 pounds per foot. The American Institute of Steel Construction, or AISC Structural Steel Handbook, lists the following cross-sectional properties. Area is 19.7 square inches. Moment of inertia with respect to the centroidal x-axis 272 inches to the fourth, and moment of inertia with respect to the centroidal y-axis 88.6 inches to the fourth. So determine the dimensions of the rectangle in figure B that has the same centroidal IX and centroidal IY as a W8 by 67 section. So this is part A. This is the wide flange W8 by 67 with these given properties here. This is the rectangular section. So the idea therefore is we equate the centroidal moment of inertia with respect to the x-axis of this wide flange section to the moment of inertia of the centroidal axis of this rectangular section. So for our solution, Ix, which is bh cubed over 12, is equal to 272. So simplifying, bh cubed is equal to 272 times 12, so that's 3,264 inches to the fourth. Call that equation 1. Likewise, moment of inertia with respect to this centroidal y-axis of the rectangular section is b cubed h over 12, and it is equated to 88.6. So therefore b cubed h is equal to 1063.2, equation 2. We then divide equation 1 by equation 2. So bh cubed over b cubed h is equal to 3264 over 1063.2. Then this results to h squared over b squared equals 3264 over 1063.2. Extracting the square root so that we can establish the relationship between h and b. So h over b is equal to square root of 3264 over 1063.2. That's 1.752. So h therefore is 1.752 of b. We then substitute this value into equation 2. So b cubed times 1.752b equals 1063.2. From here, we can now solve for b, and b is equal to 4.963 inches. Then h, which is 1.752 of b, 4.963. So h is equal to 8.695 inches. Level 84, Figure A, shows the cross-section of a column that uses a structural shape known as W8 by 67, which is a wide flange beam nominally 8 inches deep, weighing 67 pounds per foot. So that's the meaning of this. This is the depth, nominal depth, and this is the weight of the wide flange section in pounds per foot. The AISC Structural Steel Handbook lists the following cross-sectional properties. Area 19.7 square inches. Moment of inertia with respect to the centroidal x-axis 272 inches to the fourth. Moment of inertia with respect to the centroidal y-axis 88.6 inches to the fourth. Compute the dimensions of the rectangle shown in figure B that has the same radius of gyration, centroidal radius of gyration with respect to x and with respect to y as the W8 by 67 section in figure A. So for the relationship between moment of inertia and radius of gyration for our solution, I bar x is equal to radius of gyration x, k barred x square times area. So that's the relationship. 272 equals kx square times area, which is 19.7. So therefore, kx square is equal to 13.807 inches square. Then for the rectangular section, moment of inertia with respect to the centroidal axis is bh cubed over 12, and that is also kx square times area, which is bh. So bh cubed over 12 equals kx square times bh. Simplifying this, this is h square over 12 equals kx square. H square over 12 is equal to 13.807. So extracting square root, h is square root of 12 times 13.807. Square root of quantity 12 times 13.807. So from there we can solve for h. H is equal to 12.87 inches. And likewise, Iy, which is k barred y square or ky square times area, which is 19.7, and I barred y is 88.6. So from here, ky square is equal to 4.4975, equation 2. So this is k barred y supposedly for this wide flange section, but the y-axis is also the centroidal axis of this rectangular section. That's why we just equate them. So for the rectangular section, moment of inertia with respect to y-axis is b cubed h over 12, and that is ky squared times area, which is bh also. So from here, ky square is b squared over 12, and that is equated to uh, k barred y, which is equal to k barred y square 4.4975 inches square. So from here, we can solve for b square root of 12 times 4.4975. That is equal to 7.346 inches. Level 85, Figure A shows the cross-section of a column that uses structural shape known as W8 by 67, which is a wide flange beam nominally 8 inches deep, weighing 67 pounds. The American Institute of Steel Construction, or the AISC, Structural Steel Handbook, lists the following cross-sectional properties: area 19.7 square inches, I bar x to 72 inches to the fourth, and moment of inertia with respect to the centroidal y-axis is 8.6 inches to the fourth. Compute the centroidal moment of inertia with respect to x and with respect to y for the W8 by 67 shape dimension in the figure. Assume that the cross-section is composed of rectangles, neglecting the effects due to rounding of the corners. Compute your results with Compare your results with the handbook value. So this is the original section. Now, as stated in the problem, we have to consider this as component rectangles. So we ignore the rounding, the fillets in this figure. So for our solution, I will treat this as big rectangle, then less the two rectangles here. Since by symmetry, then the moment of inertia with respect to the centroidal x-axis will just be moment of inertia of big rectangle with respect to the centroidal x-axis, then minus the moment of inertia of these two rectangles with centroid lying on the same centroidal x-axis. So the width of these two rectangles would be 8.287 minus 0.575, and the height is 9 minus 2 times 0.933 inch. So that is bh cubed over 12 minus bh cubed over 12, where the base of this hollow two rectangles is 8.287 minus 0.575, while their height is 9 inches minus 2 times 0.933, while for the big rectangle it is 8.287 by 9 inches. So Ix or I bar x is 8.2879 cube over 12 minus, so this is for the big rectangle, imaginary rectangle, minus the base of the combined two rectangles is 8.287, so minus 8.287 minus 0.575 times 9 minus 2 times 0.93 quantity cube over 12. So computing I bar x is equal to I bar x Ix 270.1 inches to the fourth, which falls a little bit shorter than the actual moment of inertia of that section from the AISC Structural Steel Handbook. Then for I bar y, the moment of inertia of the big rectangle is simply 8.287 cubed by 9 over 12 less the moment of inertia of these two component rectangles, which will be transferred here at the y-axis. Or, or for simplicity, we just treat it as moment of inertia of these two component rectangles, which is passing through the centroids lie on the centroidal y-axis also. So 2 times 8.27, 8.287, 2 times quantity 8.287 cube by 0.933 over 12 plus the moment of inertia of this inner rectangle with respect to the centroidal y-axis also, which is 0.575 cube times quantity 9 minus 0.933 over 12. So Iy equals 2 times 8.287 cube times 0.933 over 12, then plus the moment of inertia of this web here, which is 0.575 cube by 9 minus 0.933 over 12. So plus 0.575 cube times 9 minus 2 times 0.933 over 12. So computing for Iy or I bar y, it is equal to 88.61 inches to the fourth, which is almost equal to this value here. So that's it for this problem. Level 86, two channels and two plates are used to form the column section shown. For B equals 200 mm, determine the moments of inertia and the radii of gyration of the combined section with respect to the centroidal x and y axis. So here is the given figure. So by symmetry, then this is the centroidal x-axis also, the centroidal y-axis. So the plates have dimensions 375 mm by 10 mm. And we need the orientation of this channel and the properties of this channel from the clip of the book by Beer and Johnson. So for our solution, here is the table, and this is the channel 250 by 22.8, and this is the orientation, and these are the properties of the channel. So the centroid of the channel is here, and its distance from this edge is denoted by barred x in this figure, and barred x is equal to 16.1, and because B is 200 mm, so half of 200 is 100, so 100 up to here plus 16.1. So the distance of the centroid of the channel from the centroidal y-axis is 116.1 as indicated or labeled here. Then the depth of this channel here is 254 mm. So the distance from the centroidal x-axis to the bottom portion of the plate, rectangular plate, or the top flange of the channel is half of 254, so that's 127 mm as shown. So IX, this IX or centroidal x-axis here passes through the centroidal x-axis of the channel. So for the channels, it is just 2 times moment of inertia with respect to the x-axis, 28 times 10 to the 6. But for these two rectangular plates, we have to transfer the moment of inertia with respect to the centroid to here. And it is equal to 375, 2 times quantity 375 times 10 cube over 12 plus area 375 times 10 distance square, where the distance of their centroid to the centroidal x-axis is 127 plus half of the thickness, so half of 10, which is 5. So Ix or I bar x is equal to 2 times 28 times 10 to the 6 for the channels. Then for the rectangular plates, 2 times moment of inertia with respect to the centroidal x-axis is base 375, height 10 cube over 12, then plus area 375 times 10, distance 127 plus 5 quantity square. So 375 times 10 cube over 12 plus 375 times 10, area of the rectangular plate, one rectangular plate, times distance of each centroid to the centroidal y-axis, 127 plus 5 quantity square. Then everything is multiplied by 2 because we have two rectangular identical plates. So computing using your calculator, it is equal to 186.7 times 10 to the 6 mm to the 4th. Then we didn't equate this to kx square, radius of gyration with respect to x-axis square, times area, where the area is area of the two channels, 2 times 2890 plus area of the rectangular plates, 2 times 375 times 10. So area is 2 times 2890 plus 2 times 375 times 10. The area of this column section, composite column section, or area of this built-up composite section is 13 to 80 mm square. Then 186.7 times 10 to the 6 equals kx square, k barred x square, or kx square, times area, which is 13 to 80. So from there, we can solve for the radius of gyration with respect to the x-axis, and it is equal to 118.6 mm. Likewise, for moment of inertia with respect to the y-axis, for the rectangular plates, there's no need to transfer because the y-axis is also the centroidal y-axis. So for the two rectangular plates, it's just 2 times 375 cube times 10 over 12. But for these channels here, we have to transfer the moment of inertia, their moments of inertia from the individual centroidal moment of inertia with respect to the y-axis, then plus area distance square, where distance is already indicated, 116.1 square. So Iy equals I barred y equals 2 times I barred y of the channel is 0.945 times 10 to the 6 plus area of the channel 2890, distance 116.1 square. So Iy equals 2 times 0.945 times 10 to the 6 plus area 2890 times distance 116.1 square. That's for the two channels. Then for the two rectangular plates, it's just 2 times, because the y-axis crosses the centroid of the rectangular plates, it's just 2 times quantity 375 cube times 10 over 12. So 2 times quantity 375 cube times 10 over 12. Combining, so Iy equals I barred y equals 167.7 times 10 to the 6 mm to the 4th. We then equate this to ky square area, or k barred y square area. area is 13 to 80. So from here we can solve the radius of gyration with respect to the centroidal y-axis. K bar y or ky equals 112.4 mm. Level 87, two angles 6 by 4 by 1/2 inch angles are welded together to form the section shown. Determine the moments of inertia and the radii of gyration of the combined section with respect to the centroidal x and y axis. So here is the orientation of the two identical angles, 6 by 4 by 1/2 angles. So for our solution, we need the location of the centroid so that we can analyze it well. So although the angles are oriented so that the orientation is such that we have this symmetrical, they are symmetrical with respect to this x-axis and y-axis, but because of the fillets, the round part, then we need to apply transfer formula for moment of inertia. So let's locate the centroid. By the way, this is part of the problem. This should be given as guide in answering this problem. So that's the orientation. So we have the centroidal x-axis, centroidal y-axis, barred x from the longer leg, barred y from the shorter leg, outer barred y. And this is the table. It should be provided so that we can analyze this problem. So angle 6 by 4 by 1/2 is this part. So the area is 4.75. With respect to the axis xx, these are the properties: I barred x, k barred x, and so on. Then with respect to the y-axis, so we have barred x and barred y also, 0.981, 1.98. So for one angle, the location of the centroid is here. So the distance from the longer leg edge is barred x from this orientation, and it is 0.981 as shown. And since the total horizontal dimension is 1/2 plus 4, 4.5, so that means half of the distance, or the distance from this edge to the y-axis is half of 4.5, so 2.25 inches as shown here. So that's 2.25. This is also 2.25. Therefore, this is 2.25 minus 0.981. Likewise, the distance of the centroid from the outer edge of the shorter flange or the leg is barred y in this designation, and barred y is equal to 1.98. So that's 1.98 inches. And take note that I'm not leveling the distance of the upper edge to the centroid or x-axis because it is obviously half of 6 inches, 3 inches. So therefore, this vertical distance is 3 minus 1.98 inches. So for Ix, this is the centroidal x-axis of the angle, which is the same as this, or this centroid here. So we have to transfer the moment of inertia. So 2 times moment of inertia with respect to the centroidal x-axis of one angle, which is 17.3, then plus area, which is 4.75, distance, quantity 3 inches minus 1.98 square. So this is 3 minus 1.98 square. So Ix is equal to 2 times quantity, I barred x, 17.3 for one angle, then plus area 4.75, then distance between this centroid and this centroid here, 3 minus 1.98, then quantity square. So solving for Ix or I barred x, it is equal to 44.48 inches to the fourth. For the moment of inertia with respect to the y-axis, this one. By the way, for the radius of gyration, we equate this to uh, k barred x square area, where area is 2 times 4.75, so 9.5. So 44.8 I barred x equals k barred x or kx square in this case times area 9.5. So kx or k barred x is equal to 2.164 inches. Likewise for Iy, so we have to transfer the moment of inertia of this angle with respect to the centroidal y-axis to the centroidal y-axis of the entire area. So that is 2 times quantity I barred y of the angle is 6.22 plus area 4.75. Then this distance quantity square is 2.25 minus 0.981 quantity square. So I barred y or Iy equals 2 times quantity 6.22 plus area 4.75, then square of this distance. This is the centroidal y-axis and this is the centroidal y-axis of the entire region. So this is 2.25 minus 0.981 quantity square. So Iy or I barred y is equal to 27.74 inches to the fourth. We then equate that to ky square area 9.5. So ky or k barred y can now be computed and it is equal to 1.709 inches.